In this video, I'm going to be showing you how you can simulate a waveguide in a baffle or in a loudspeaker cabinet. So for this, I've prepared just a simple mesh file of a rectangular waveguide, which we can simulate in quarter symmetry mode. Now, while I'm going to use quarter symmetry in this example, this works perfectly fine for half symmetry as well. So, for example, if you have a cabinet which is only symmetrical in one axis, it's basically the same thing. The only thing you have to change is when we choose the symmetry. I'll talk about that later. So to start with, I'm going to open the Components tab and I'm going to import a mesh file. In this case, the mesh file is in cabinet, and we're going to scale it as we've done in our other examples, 1 millimeter, click apply, and here we have it. Now, this waveguide and cabinet has a very low resolution. This is going to give substantial issues pretty low in frequency. So the reason I've done it this way is simply because I want the calculation time to be as short as possible just for this example. If you were to draw or simulate something, which is for tweeter applications, you really should use a higher mesh density than this. So just be aware of that. This mesh density is not sufficient. It's not even close to sufficient. So to begin with, I've made the model such that there's nothing we need to remove. Everything is meshed as it should be. So all of these should be selected. So we can just click apply, and then we can close this. Now next, we're going to model everything as an exterior domain. It's best to model everything as an exterior domain if you can get away with it, in my experience. So we're going to do that. So we're going to click on subdomain, and we're going to create an exterior domain. Going to click apply and close this. Now we have our subdomain, and that's really all we need. Next up, we go to Elements Mesh File, and then we go to Drawing, and we basically just click on this. This is the diaphragm. This is tag 6. So we're going to remove this, and then everything else we're going to leave selected. We click apply, and now we have the drawing. This is basically going to be the exterior. This is the part that's not driven. This is just a hard surface, and that's completely fine. So now that that's in place, we can just close this, and we go back to Elements Mesh File. We create a new one, which is going to be our driver. And in this case, we unselect everything except this part number 6. And then we go to Boundaries, and we choose Driven, and we choose Direction Normal to Surface. That is the correct thing to choose for compression driver. So since this is a flat disk, we're simulating a compression driver in this case. An idealized one, mind you, but still a compression driver. So once we've done this, we can give it a name if we want. We can call this diaphragm, for example. Click apply, and we can close it. So now we have our driven element in red, and we have our boundaries in gray. Now, the next step is to actually choose the symmetry. So to do that, we go to Global, and we go to BEM Parameters. And on Symmetry, we choose, I believe, XY. So it's going to be symmetrical across here, across the Y-axis, and across the X-axis, like so. And now it's starting to look like something. This is what you'd be used to seeing. But once again, this is very low resolution. The details of the horn are even wrong at the throat. It looks like there's a sharp step here, while in reality the model is continuous. It's smooth. So these results are going to be very inaccurate above just a couple of kilohertz. Now we've done this, and now we have to choose the frequencies which we are interested in. So we're going to frequencies, and in this case, I can just completely forget about simulating up to 20K. Let's just say 10K. It's not going to give accurate results up to that frequency either, but let's say we do 500 to 10 kilohertz, for example. Click OK, and now we have our frequencies here. And the next part is simply to add our observation points. So we can go to observations here in the components tab and choose radiation polar, because that's probably the most interesting part. And here we can see that it's wrong. The on-axis is 90 degrees to the side, which is wrong. So we go to position and we choose instead CX, right? And that's the horizontal plane. So we're just going to call this radiation horizontal. Click apply, and then we choose parameters. I'm going to simulate around the whole cabinet in 5-degree steps. And I'm going to normalize it because we don't have a lumped element model for the compression driver. I'm not going to model the compression driver with lumped elements. So what we're interested in is the normalized radiation polar. So I'm going to click apply. Now it's normalized to 0 degrees, and I'm just going to choose, let's say, a 3-meter distance. So that's good. And then now I'm just going to copy this. Just copy and paste. And then this one is going to be radiation vertical. And in this case, I'm just going to change the position. So it's going to be CY instead. So now we can see that's the vertical. So now and everything else is the same because we copied the first one. So the distance is the same, the normalization is the same, the increments for the angle is the same, and we're also going around the whole thing. All right, so now we've done that. And the next part, we may be interested in the radiation impedance, for example. So we click radiation impedance, we choose the mesh file, click apply. And I think that's about it. If you want to, you can add fields as well to try and visualize how the driver radiates sound. You can add, for example, a fields shell in the horizontal plane or in the vertical plane if you want, as I've shown how you can do that in the 2D room video or in the bass reflex loudspeaker video. So have a look at those if you're curious about how fields work or how you can add a field. Now that we've done that and we're more or less ready to simulate, the only thing we need to do is we need to make sure we set fixed driving. So we go to global, we go to fixed driving, we enable it, and then since we're just looking at the normalized radiation polars, the kind of driving we use doesn't actually matter, because the driving affects the on-axis frequency response, or the frequency response of the driving element. But since we're normalizing to the on-axis, it's just the relative difference between on and off-axis which matters, and the driving does not affect that. So we can leave it on as unchanged. There's no problem with that. Click apply, and now we can simulate. So we could just go to processing and choose calculate all. And now we can see it's 980 elements. That's not very much. Just going to let this solve. It may take a little bit of time, but that is perfectly fine. So now it's pretty much done with the first 32 frequencies. So it's going to do the next 32. You can see down here actually that it has CPUs 32 out of 32, and that's the amount of logical processors it has available. So in this case, it just means that my CPU has 32 threads available for simulation. And there it's done. So now I can open VAX. And here we have the radiation impedance. It looks a little bit strange. There's a bit of a peak at around 9 kilohertz, which is most likely due to this sudden step in the throat. Since the throat has not been modeled properly, it needs higher mesh resolution to actually look geometrically correct. But the radiation impedance looks like so, and if we look at the polar, here we have the horizontal polar. Looks pretty good. It's not terrible. It has some waist bending, but it's not too bad after all. But we can see that the frequency response is a bit jagged as you move off axis. There are definitely some numerical errors here. And then if we look at the radiation vertically, it looks like this. So it's a bit more beamy, as we can see, but it looks not too bad here either. Of course, it's kind of hard to trust these when the mesh resolution is so low. But this is the basic premise of how you will simulate a waveguide in a cabinet. And as mentioned, this works perfectly fine if you have, for example, an asymmetrical waveguide where you have a different radiation pattern in the vertical plane for up and down, for example. In that case, the difference would mostly be just that you're going to BEM parameters, that you're going to BEM parameters and you're choosing a different symmetry setting. But otherwise, everything else is the same. Thank you very much.